Hey, welcome back. Today we're going to do something a little bit different. Instead of covering lessons one at a time, we're going to walk through them all at once. We'll start troubleshooting an application problem, then some general TLS issues and certificates. Next, we'll see some security anomalies and NMAP scanning. And finally, a few more real-world scenarios. If you've been with the channel for a while, you'll recognize some of these lessons. Between sections, I'll jump in with a few tips or something else to say here and there. This is one of those sessions you may want to save because issues like these tend to come back again and again. So let me set up the scenario here. We've got an application that's not working properly that uses port 80 HTTP, and the apps department doesn't know why it's not working, and they need some help with it. So we've got a packet capture that we've taken here. Our job is to take a look at it and see what the problem is. Well, the first thing I would normally say would be, okay, let's filter by the source and the destination IP. But in this case, we don't know what the destination IP is. All we have is a URL to go by. So the URL is www.LanWanNinja. In this case, it's my website that we're using here. So let's go ahead and get started. So the first thing we're going to do here, since all we know is the URL, we're going to type in just DNS. So we just filtered by DNS. We put DNS in the filter box, and there's still a lot of stuff there. If you look down at the bottom of the screen, it says there's still 84 packets. Let's make it a little bit easier. So we've clicked on one of these DNS packets. Over here on the left-hand side of the screen, we're actually going to find that DNS query. In this case, it's accounts.google.com. I'm going to right-click on that and go to Prepare as Filter. So we're going to do Prepare as Filter, selected, and then we're going to go up to the filter box here and actually edit that. What we're going to do is we're going to change that to www.LanWan.Ninja and then hit enter. We've just taken those 84 DNS packets and reduced it to just 8. So now with just 8 DNS packets, it's pretty easy to see what our destination IP address is. So we can tell in this case, it's 192.168.1.166. So let's go back up to our filter box here and type in what I already know my source address is, which is ip.addr = 192.168.1.158. Then we're going to put and ip.addr = 192.168.1.166 and hit enter. So now we've distilled that traffic down to only traffic between those two devices. The first thing I see here is another problem. There's a bunch of DNS packets. Since we have our destination IP already, we don't need to see all these DNS queries. So now let's type and not the exclamation point DNS. So we've taken out all the DNS packets. Now what do we see? Well, remember I said this is port 80 that the application department have said that their app uses. What we're seeing here is the behavior of our web browser. If you notice here, in this very first packet, the destination port is 443. Well, we didn't put in HTTPS and we didn't tell it to use port 443, but the browser is going to automatically try to use 443 because it wants to use an encrypted port and it wants to encrypt the traffic. In our case, though, the web server is not responding on 443. Another thing to notice here is our source port is 58528 and our destination port is 443. This source port, port 58528, is called an ephemeral port. Now, this is another concept that I struggled with at first, but again, it doesn't have to be hard. An ephemeral port is just a random port that the originating computer makes up to use as a source port. That's it. Most of the time, this port is in the range of 49152 through 65535. But back to this first packet, we see our computer sending a send packet, and instead of just sending an ACK packet back, the server is sending back an ACK and reset. So it's ACKing the connection, but it's also closing it with the reset. One more thing to notice here, you see that we have source port 58528 and destination port 443. You notice on the return packet, port 443 becomes the source port from the server, and our 58528 becomes the destination port. And we can see this process repeat itself several times. The client comes in on port 443 looking for an encrypted connection, and the server says, no. So what's our next step now? Let's get rid of these port 443 packets. What I'm going to type is and not tcp.port equals 443. So now we're really getting down to what we want to see. We've got it filtered down now to 184 packets. So if we notice here, let's look for our three-way handshake. We see the send packet coming from us on this port 58534. Next, we see a SYNAC packet coming back from the server, again on that port 58534. And then we see an ACK packet coming from us. I'm going to take this first packet and I'm going to use a comment. I'm going to add new comment and I'm going to say three-way handshake and hit OK. Well, that's great that it displays it here in our packet comments section of the packet details, but we need to see it on the screen, right? So let's do that. I'm going to click on three-way handshake here, going to right click, and I'm going to say apply as column. So now we can see our comment as a column in our packet list. I'm also going to use another really good feature here. I'm going to right click on this packet and I'm going to mark it. What we're really interested in here is seeing the HTTP gets and posts and their replies. So let's just think of all the ACKs and SYNACs and everything like that for now as TCP housekeeping. Here's the GET request where our client is requesting what's at the root of the web server. We'll go all the way over to the left here and see the arrow pointing to the right is our request. And if we look down here just a little bit, the arrow pointing back to the left is the reply. So we see the reply 302 found. It looks like the web server replied and no issues. Next, we see get login.php. So it looks like to me that this is where the server is requesting us to log in. That seems important. So again, I'm going to add a comment. The comment I'm adding is just login request. And you can see my comment is displayed there. Scroll down here a little bit more and we see a post. So in this case, this post is the application logging in. So let's scroll down into the packet details and we can see here where the application is logging in. We see username with the value of admin and password with the value of password. Yikes, that's not a very secure password. Let's also think about this. We're just seeing network traffic, and we can see that password. Sending Cleartext passwords over the network is never a good idea. You don't want this guy on your network looking at all your passwords, do you? I'm going to comment the post as appcred sent Cleartext. So if we keep following through here, we see a get index.php and look over and see the reply, HTTP 200, okay. We see a get vulnerabilities brute, HTTP 200, okay. So everything's looking good up to this point. We're seeing requests and we're seeing replies. If we look down at the bottom of the screen again, we've still got 184 packets to go through. And a lot of those packets are this TCP housekeeping that we're calling it for now, where we're seeing the ACK packets, SYN packets, etc. And that's not to say that the problem can't be in those packets, because it can, just not this time. Can we filter it down some more is the real question. And the answer is yes, we can. Because what I'd really like to see here is I would like to see just the HTTP requests and replies only. So to get the HTTP requests, I'm going to add and http.request. That's close to what I want to see, but that doesn't tell me anything about the replies. So let's also add in here the HTTP replies. The way we're going to do that is right after the and in our filter, we're going to put an open parentheses, http.request, then we're going to put or http.request _ in and close parentheses and hit enter. This is the filter that I was talking about that's going to give us all the HTTP requests and their replies. Here's the reason why it works. If we go here to a request, we can see request method get. If we're going to act like we're adding a filter and go to apply as filter, you can see that says HTTP request method equals get. We are just deleting the end of that and leaving HTTP request. That's the first part of the filter. If we go to a reply here, which this next one is the reply, scroll down a little bit here, we see this line right here that says request in frame. We right click on that and act like we were adding a filter. We can see apply as filter http.request _ in. We're just taking off the last part of it, and we're saying that that packet is an HTTP reply to a request in this capture. So now that we've got this filtered down to just 46 packets, let's step through and look at a couple more things and try to find out where that application problem really is. We see a get index.php and the reply to it says, okay, that's good. An HTTP 200 normally means there's not an error there. So we see a get vulnerabilities brute, HTTP okay. We see get vulnerabilities exec, HTTP 200 okay. We've got get PHP info okay, vulnerabilities okay. And I'm just going to kind of scroll down a little bit here, because if we're seeing an HTTP HTTP 200 coming back, it's probably fine. Now, there still could be some kind of error in it, but that's not what we're looking for here. It's not sending bad data. It's just broken. So if we keep scrolling down here, get, and then to 200 OK, get 200 OK, get vulnerabilities, application function.php, HTTP 1.1 404 not found. So this is really what we're looking for here. Again, we talked about an application that's not working, that's talking to a web server, and it's looking for something that's listed under vulnerabilities/application function.php, and that's not on the server. So in our case, this is our problem here. Is there something wrong with the web server? I don't know. Is there something wrong with the client app? I don't know. Maybe they're on two different versions, but this is what's causing the problem. This is why that client app just stops working, or some function of the client app stops working. So we've now found what we were looking for. So now that we've found this packet, let's also mark it with a comment. I'm going to add the comment application function.php not found. And I'm going to go ahead and mark both of these packets. So I'm going to look at my packet details window here and zero in on this status code equals 404. I'm going to right click and go to Apply as filter and select it. So you'll notice here that shows us a 404. To make this a more versatile filter, I want to remove the HTTP request, and instead of a response code equals 404, I'm going to add in a response code greater than 200. Since we know that 200 is HTTP OK, a lot of what comes after 200 are redirects and errors. So that really zoned in on our packet, and maybe we would use that if we were just looking for redirects or errors. Maybe that's the filter that we would use. But as you notice, it doesn't give us that full view of everything that was going on between the client and the server. So one last filter here that I will show you is to filter on only our comments. So let's say we were going to send this packet capture back to the apps team and we wanted our comments on there. We're going to take the start of our filter here and then add and frame.comment and hit enter. So now we get just our commented packets. And if we wanted to export those and send them to the apps team, we just go to File, Export Specified Packets, All Packets, Displayed, and then just give it a name. In this case, let's call it PCAP for apps team. So now we just exported just those 4 packets, so the apps team can see exactly where the problem is. For this next section, let's look at TLS connections, because those always work. Right? Let's start by talking about TLS and SSL issues. Some examples of these issues you may see might be an encrypted website you browse that starts with https:// and it gives you some kind of encryption error. Or the issue might be a function running on an application server that's getting data from another web server. And that function has failed, probably with a nondescript error message. There are many issues that can cause TLS or SSL to fail, but we're just going to look at some of the most common ones and how to find and troubleshoot them with Wireshark. TLS is Transport Layer Security. SSL is Secure Sockets Layer, which is a similar older version. TLS is the encryption protocol used to secure websites, applications, email, VPN connections, etc. For now, I'll just refer to it as TLS, although the acronyms TLS and SSL are many times used interchangeably, even though SSL is really the older technology. We do need to talk about security within TLS though. If you or the websites you support are not using TLS version 1.2 or version 1.3, they need to be. And you really need to turn off support for TLS version 1.1, 1.0, and SSL version 3. Notice that the ones on top, SSL 3 and all previous versions, TLS version 1.0 and TLS version 1.1. These have been deprecated because they're no longer considered secure. There are various attacks that these are susceptible to. A few of the notable ones are Poodle, Beast, Freak, Logjam, and Suite 32. Just do a web search for more info on any of these. Also, when we're looking at the list here, keep in mind that most modern browsers by default will only support TLS 1.2 and 1.3, which is another reason why you should only be using those 2 versions. So within Wireshark, looking at the packets, what does a successful TLS handshake look like? At the top in the graphic here, you can look over here in the info column. We'll just go through that. You see the client hello, server server hello, certificate status, key exchange, server hello done, client key exchange, change cipherspec, encrypted handshake message from the server. Down below here, this is a typical successful TLS version 1.3 connection. Client hello, server hello, change cipherspec, application data, and then a packet back from the client that says change cipherspec, application data. If you notice on this second one, the TLS 1.3 connection, everything looks duplicated, and the reason that is because this is actually two different connections. In the first packet, you can see the packet going from the client to the server with a source port of 45117. The third packet is also part of that connection. You see the destination port in that packet going back to the client at 45117. Then in the last packet, again coming from the client with a source port of 45117. So all of them that you see here with 45117 are one connection, and the ones with 45118 are another connection. The reason that there are two client hellos, two server hellos, etc., are that there are two connections and they both do need to be secured. TLS versions and cipher suite mismatches are the most common non-certificate issues that I see. Certificate issues will be another video all their own. If you look in the filter box here, this is the filter that we'll be using mostly today. We also may add an IP address to it, but this is my favorite one for TLS troubleshooting. So let's find out where we need to look in this packet capture. Again, we don't know exactly what packet where the problem starts, but we do know the name of the domain is badssl.com. That's where our user or application was having an issue. By the way, badssl.com is a great website if you need to test TLS with your web browser. Or it's also great if you want to do Wireshark captures of TLS connections on your own. So first, let's find out where our issue starts by looking for DNS packets. If a computer does not know the IP address, when it looks for badssl.com, it will have to query a DNS server first. This is how we know where the issue starts. So we're going to type in dns.qry.name equals quote badssl.com. End quote. So I see right here where the client queried for badssl.com. I'm going to mark this packet and I'm going to comment on this packet, and I'm just going to say DNS query. I'm also going to note down the IP address here, which is 104.154.89.105. So now let me show you another trick that I sometimes use to mark a capture in Wireshark while the Wireshark capture is in progress. When I was running this capture, I used single ping packets to mark the capture in several places. I pinged my default gateway and varied the packet length each time. I would send a ping and then immediately test what I needed to. This way I knew right where my ping was the exact point that I started my testing. So back when I ran this capture, here's what I did. I want to ping 192.168.1.1 and use a -n space 1, which will mean just one ping, and -l space 300. This will make the data portion of the ICMP packet equal 300 bytes. So as you can see, one ping. And that's what I've used to mark this capture. In this case, I did one with a data length of 300. I did another one with an ICMP data length of 400, and then another one with 500. So those are the three pings that I did in various places. So the filter that I'm going to use here to find these packets is ICMP and data.len greater than or equal to 300. So you can see the ping and the reply for each of these pings. If you'll notice here, here's the data length of 300. But if we look at the length of the actual packet, it is 342, 442, and 542. I want to briefly show you why that is. And I'm going to go over this quickly, so if you want to pause it and look at it, go right ahead. So we saw that our total packet length was 342 bytes, but our data that we added to that ping was only 300. What it is there's an Ethernet header of 14 bytes. There's an IPv4 header of, in this case, 20 bytes, and most of the time that's what it is, but it can be bigger than that. And then the ICMP header of 8 bytes. So if you take 14 plus 20 plus 8 plus our 300, then you get the 342. And that's why the total packet length is 342 bytes. But back to our pings here. I want to mark each of our pings, and then I want to comment on each of our pings also. So I'm going to go to packet comments, add new comment, and just put in first ping 300 for the second ping request that we sent out. Add new comment, second ping 400, and the last one, third ping 500. Just remember that each of these pings lines up exactly with what we were testing because it was done right before. So we're using here our TLS troubleshooting filter. That again is on my Wireshark display filters cheat sheet. We're going to add two things to this filter though. We're going to add and ip.addr = 104.154.89.105. That's going to show us packets only to or from that IP address. And that's the IP address that we got from our DNS packet for badssl.com. The other thing that we're going to add here, so that we can see our commented frames, we're going to add or frame.comment. So if you look at the bottom of the screen, out of 4,425 packets, we've got it down to 181. And since we have our comments added, it's going to make this pretty manageable. So there's our DNS query. Let's scroll down to where our first ping starts. And right after that, we see a client hello from the client. The next packet that's listed is a server hello from the server, and then an alert. The alert says fatal description protocol version. So for the quick solution, go to the alert packet, and we see the alert message, level fatal, description is protocol version, and then version TLS 1.0. Well, this is great, but it's not going to help us talk to the apps team or the software vendor. We need a detailed reason why it failed. So let's look at the client hello. If we scroll down here in packet details, handshake protocol, client hello, and then if we look down here to extension supported versions, it says TLS 1.3 and 1.2. This is what the client supports. The client in this client hello packet is saying, I support TLS version 1.3 and 1.2. Now let's go to the server hello. We see the version number in the handshake protocol, TLS 1.0. So this is really the root of the problem here. The server is only going to use TLS 1.0, which is not considered secure. And it's subject to man-in-the-middle attacks.
Hey, hey, be quiet. I'm listening.
Since the client only supports version 1.2, or 1.3, here's what we're going to tell the apps team or the software vendor. We're going to give them the host name, the IP address, and the port number, and we're going to tell them that this server is only supporting TLS version 1.0. That's why people are getting errors, or that's why your app function is not working. The other thing that we'll give them, if applicable, is the full URL that we were trying to hit at the time. All of these details are important, or without them, they might not be able to find that web instance. They might have many web instances on that server. If we give them all the information, then they can find the one that needs to be fixed. Well, let's assume that you told the vendor about the issue, they found the problem, and they fixed it, or at least they think they fixed it. The second ping here is where we tried again. So what we see this time, we see the client hello, the server hello, and the alert level fatal description protocol version. Kind of similar to the first time, but let's see if it changed any this time. In the client hello, we see under the TLS record layer, we see version TLS 1.0. This field right here can sometimes be misleading. I would say to always look in the handshake protocol client hello if you're looking for version or supported versions. In the supported versions, we've got TLS 1.3 and TLS 1.2. It's going to look the same as it did before because it's the same client. On the server side, we see, again, in the handshake protocol section, we see version TLS 1.1. While this is a step forward from the application vendor, TLS 1.1 is also not considered secure.
I'm listening.
I also want to close in just a little bit on this particular connection where the client source port is 49408. I'm going to add a filter here of tcp.port equals 49408. So when we look at this, we see client hello, server hello, alert fatal, and then after that, the server sends its certificate and exchanges its public key and says, hey, server hello done. In the big list of packets, it might be easy to miss that alert level fatal and just see the certificate and server key exchange server hello done and think, oh, hey, it's working. But that's not the case here. So let's remove the tcp.port equals 49408 and go back out to our big list of packets. Let's look at the very next packet after the server is sending its public key. The client increments its ephemeral port from 49408 to 49409 and sends another hello. And this continues several times. But since they can't agree on a version, server sending TLS 1.1 and the client only supports 1.2 or 1.3, the TLS connection never gets established. So we talk to the vendor again, they get back to us, and they assure us that they have fixed it this time. So we try it again, and that's where our third ping is, on our third try. So we look right after our third ping, and we see, just like before, supported versions, TLS 1.3, TLS 1.2. We look at the server hello, and we see version TLS 1.2. So they both support 1.2, and in this case, they agree on everything else, so that's great. Yay! TLS 1.2 still works, but TLS 1.3 is faster and it's more secure. but it's good enough for now. Most modern browsers support it. But something to think about, version 1.2 was designed in 2008, and 1.3 was designed in 2018, so it will definitely be secure for longer. So following through with the rest of this connection, we look right here, the server sends its certificate, server key exchange, the client key exchange, and new session ticket, change cipher spec, encrypted handshake message. So at this point, we have a good TLS connection. Version 1.2, but hey, sometimes that's the best you're going to get, and we can be okay with it for now. Yay! Okay, so that was the TLS side of things. But next we'll see that getting through the handshake is really only half the battle. Here's where things get interesting. What happens when an application works on most machines, but a few of them just refuse to run it? The logs don't help, and of course the vendor blames your network. Server certificates are the other part of TLS that we did not talk about in the last video. So what are certificates? I'm going to simplify the explanation here to talk about their use in TLS. A server certificate is a digital credential that authenticates and encrypts communications between a server and a client over the internet. For authentication, a server cert lets us be sure that the server is who it says it is. And for encryption, the server cert encrypts data only during the initial key exchange in TLS. Then TLS takes over. On the screen, I have a certificate from Microsoft that I've exported. So what are the major components of a certificate? The subject, issued to, which is the server or website name. The issuer, you can see here it's issued by, and that is the certificate authority or CA that issued the cert. Next, we have the validity period. What is the first date it is valid? And what is the last date it's valid? And what we also see here is the public key. It's used by clients during the key exchange to encrypt data sent to the server, and the server uses its private key to decrypt this data. And lastly, we have the SAN, or Subject Alternative Name. This allows a certificate to specify additional host names, IP addresses, or domains that are valid for this cert. So how do we know that we should trust a cert? That's a good question. The answer is that we don't trust certs directly, but we trust who issued them. Each cert is issued by a certificate authority, or CA for short. A simplified definition for a CA is that they issue, store, and revoke certificates. Next question, how do we know we should trust a CA? These CAs that typically issue certs to servers or websites are called intermediate CAs. Their certificates are typically issued by root CAs, and we trust the root CAs. So getting to the root of the matter here, we trust the root CAs because there are lists of trusted root CAs from operating systems like Microsoft, Linux distributions, and Apple. Also, browsers and app vendors like Google and Mozilla, and Oracle for Java. These lists of trusted root CAs are what we trust. Now, because we trust the root CAs, we also trust any CA that they issue a certificate to, or server certs that these CAs issue. So we trust any cert issued by any CA as long as it can be traced back to a trusted root CA. I think this will make a little bit more sense when we dig a little bit deeper into certificates. So now let me show you how I exported these certificates earlier. Let's go to www.microsoft.com and look at its certificate. I'm going to click on View Site Info and select Connection is secure. And I'll click where it says certificate is valid. Then I want to click on Details and make sure Microsoft is selected, and then click on Export and add .crt to the end of the file name, and then click Save. So now I'll open that CRT file, and we can see validity, issued to, and issued by. If we click on Certification Path, we can see the cert, www.microsoft.com, was issued by, the one right above it, Microsoft Azure RSA TLS Issuing CA 07. That's the intermediate CA. And that cert was issued by DigiCert Global Root G2. That is the root CA. On any of these, we can click on View Certificate and see those certificates also. I have one last thing to show you here while we're talking about certificates. It's the list of trusted root CAs in Windows. So what we're going to do is we're going to go to Start and then start typing MMC and then click MMC. This is the Microsoft Management Console. So it's going to ask you, do you want to allow this app to make changes to your device? And just click Yes. So now we're going to click on File and Add Remove Snap-in, click on Certificates, and then click on Add and select Computer Account. One thing to know here, if you don't have admin access on this computer, you will not see Computer Account. So now we're going to click Next, and then we're going to click Finish. And now that you see certificates there, we're going to click OK. So expand certificates, expand Trusted Root Certification Authorities, and click on certificates. You can look through this list, and these are all the root CAs that Windows trusts by default. Now click on a certificate and look down at the bottom of this window. It should say Trusted Root Certification Authorities store contains this many certificates. If this number is, let's say, less than 400, you may not have the entire current list from Microsoft. So now that we know how certs and CAs work, let's troubleshoot some more TLS in Wireshark. But this time, we will be focusing on certificate issues. Scenario number 1. We have an internal application that's having issues. When users click on the application, they get an error message that says, server not responding. You've checked the log files, and of course, they tell you nothing. So you decide to talk to the application team, and they tell you everything looks fine on their end. They also remind you that the last time we saw this error, it was a network issue. You run an NMAP scan on the server, and the server ports that should be open are open. You don't think it's a network issue, so you get a packet capture on a PC. Before we get started, let's check one setting in Wireshark. If we're dealing with certificates like we are today, it's important to make sure we have this setting set correctly. If you go to Edit and then Preferences, expand Protocols, and go all the way down to TCP, and make sure that this setting right here, this Allow Subdissector to Reassemble TCP Streams, is checked. And then click OK. I also want to show you two things that we're going to do to prep for taking this capture. The first thing that we're going to do is an ipconfig-flushdns. So from a command prompt, I simply type ipconfig-flushdns and then hit enter. The reason that we're clearing the local DNS cache is that we want to see the DNS resolution in our capture. This will help us locate the point where our application opens and starts to communicate, but it will also make sure that DNS is pointing to the correct IP. The next thing that we want to do is mark our running capture with a ping packet. Now I've got my 500 byte ping ready here. I've got a -N1, so it'll be one ping, and I've got a -L500, so it'll be 500 bytes long. So what I'm going to do here is I'm going to start the capture. I'm going to hit enter on the 500 byte ping. Then I'm immediately going to test my application, and I'm clicking on it now. As soon as the error message comes up, then I will stop the capture. So let's start with DNS. I'll type dns.qry.name contains badssl.com, since that's the domain name we're using to demonstrate in this capture. Now, technically, this scenario is about an internal application, so in that case, we would have said contains and then our internal server name. This first packet here is where our computer sent a DNS query to find the IP of the application server. Now let's mark this packet. So I'm going to right click and mark, and I'm also going to right click and packet comments, add new comment, and I'm going to say DNS query our app. Now let's filter by ping size and find our ping packet. So here I'm going to type icmp and data.len is greater than or equal to 500. There's our ping marking where we started our testing. I'll put in a comment here, packet comments, add new comment, that says ping 500. So now let's look at the capture with only the IP address from our DNS query. Let's put in the filter ip.addr equal 104.154.89.105. What I want to do here is add another coloring rule. So I'm going to go to View and then Coloring Rules. I'm going to click the plus sign, and for the name of the coloring rule, I'm going to put in TLS. For the filter that I want to use, I'll also put in TLS. And I'm going to click Background. What I want to do is make it just a little bit darker than a regular TCP packet, and then click OK, and then click OK again. There, that's what we want. Now the TLS traffic stands out just a little bit from our regular TCP packets. Now let's put in our TLS troubleshooting filter, and I'll also leave this filter in the description. Let's also now add our IP address. So I'm going to type and ip.addr equal, and remember this is our IP address from our DNS packet, 104.154.89.105. And then let's also add our comments. So I'm going to type or frame.comment. So what this filter says is that we want all of our TLS packets, and we want to see that IP address from our DNS query, or we want any frame that has a comment. And so now you can see here our DNS query and where we have our 500 byte ping where our testing started. We can see the TCP source port of our client hello right below where our testing started is 52280. Let's add this to our filter so that we can get this conversation only. Now to do this correctly, we need to add tcp.port equals 52280 before our frame.comment. So I'm going to add that now. So I'm going to type in and tcp.port equal 52280. So if we look at the TLS portion of that conversation, it really looks like a normal TLS exchange except for that encrypted alert. We don't see an alert level fatal or any other errors like we did in the last video when we had TLS protocol version issues. It looks kind of like a good TLS connection, except we know that it's not working. So let's back out a little bit from our very filtered close view here and see the whole of this conversation with the source port of 52880. Here's something new that I haven't introduced yet, but it's a very useful command. I'll right-click on this first packet, our client hello with the source port of 52280, and then I'll select follow TCP stream. A lot of the time, this first window is the best part. You can see the text of all the communications between client and server in this TCP stream. So this time when I'm looking at this, I notice the words Komodo, RSA domain validation, so I know that there are some certs in this stream. But this time we're going to close this window by clicking on the X in the upper right corner. Now let's look at our display filter. It says TCP stream equals 102. Whenever you click on follow TCP stream and then close the window, Wireshark will always change your display filter to only display that TCP stream. Sometimes this will mess you up, but this time it's exactly what we want. So let's look at the first three packets here. SYN, SYNAC, ACK. This is our three-way handshake. As we look at this, let's remember that everything that is not dark blue is not being displayed by our normal TLS troubleshooting filter. Well, now that part is going to help us solve the issue. We see our client hello, then our server hello, certificate, client key exchange, then encrypted alert. Right after that, we see that the client sends a FINAC. In simplified terms, the client is requesting a graceful shutdown of the connection. Next, we see a duplicate ACK. This means the server is retransmitting an ACK packet that it's already sent. We see a few more ACK packets, and then a packet from the server that says new session ticket, change cipher spec. So the server is just going on like everything's good, but it's not. So now let's look at the bold red packet there. That is a reset packet. The source address is the client, and reset means close the connection now. But the server's still not listening and sends a duplicate ACK packet, and then it retransmits a 312-byte packet 5 times. If we look up just a bit, we see that it's packet 5363, the new session ticket. Now remember, all of this is happening after the client sent that reset. Whenever I see a reset packet, I first check to see if it came from the client or the server. I want to know who didn't like what they saw. Also, I want to know when they sent it. Do we see any packets that say TLS application data, like this connection? Here, we do see TLS application data packets. All of them are 200 bytes or more, so we know there's a decent amount of actual data in there. Back to our current capture. Number one, we see that the client sent the reset packet, and we notice that it happened after the server sent its cert. And we don't see any encrypted traffic, like the TLS connection was never completely set up. I'm starting to think that there's something wrong with the certificate based on what we're seeing. But since this is an internal application, we need something solid to send to the apps team. So let's prove it. I've added a few comments to the packets here in case you want to screenshot it for a later reference. So since we think it is the certificate, let's take a look at that certificate. First, I'm going to go up to the packet where the server sends the certificate, click on it, and then go down to packet details. I click on the transport layer security fields, and then I'll click on TLS v1.2 record layer handshake protocol certificate. Then down below that, I'll click on Handshake Protocol Certificate, and then I'll click on Certificates. Now, if you look here, we see 3 certs altogether. To save these certs, right where it says Certificate Truncated, I'm going to right-click. I'm going to go to Export Packet Bytes. And when that window pops up, I'm going to note down where I'm saving this. And I'm going to name the file cert1.crt. The CRT extension is important because it will let Windows open the cert when you click on it. So I'm going to click Enter here. I'm going to go to the next certificate where it says Certificate Truncated, Export Packet Bytes, and I'm going to name this one cert2.crt. Next, I'll do the same thing with the third cert, and I'll name it cert3.crt. Now I'm going to go to the directory where I saved the certs and open them up by double-clicking on each of them. The cert1, cert2, and cert3. The first cert is issued to badssl.com. That is the cert for the actual web server. And just look at the valid from there. 4/8/2015 through 4/12/2015. Wow, it's a cert that's only valid for 4 days. Notice here that it says the certificate has expired or is not yet valid. And also notice the red X on it here. So this is our issue right here. This cert is expired. That's what was causing the generic server not responding error. So we know that the actual server cert is expired, but let's look at the rest of the certs in its path to a trusted root. I'm going to click on certification path. Its intermediate cert looks good. And also notice that the intermediate cert is here, cert number 2. And we also see on both of these that the root cert is named Sectigo formerly Komodo CA. And again, Windows is not displaying a red X. So that cert is in our trusted root store, and therefore we trust it. If we look at the cert on the right here, cert number 3 that the web server sent to us, it's valid only until 5/30/2020. So it looks like it's an old cert for that same intermediate CA. If we click on cert path on this one, we can see 2 red X's. So this certificate and its root cert are both expired. We also want the apps team to get rid of this old expired cert. It's not the root of our problems here, but it can only cause problems later. So now that we know the problem, we send the cert1.crt file over to the apps team along with the commented PCAP so they can see that the cert is bad, and they fix the issue by getting a new cert issued. And they also get rid of the old expired cert. Just a quick security tip here. I sometimes see companies training users just to click through cert errors for internal web applications, rather than fixing certificates. This is not a good security practice. If the users get used to clicking on bad certificates like that, they're going to click on something from the bad guys, like these two.
Hey, don't listen to him. Teach him to click on everything. Yeah, and use default passwords too. We like looking at your data.
Scenario number 2. Okay, one more scenario, and I'm going to speed this one up since it's a lot like the last one. You have a desktop app that's working fine for 5 people, but not working at all for 2 people. They are getting a connection error as soon as the app loads. You call the app vendor and they say it's your issue. Probably it's your firewall blocking the traffic. Since there are only 2 people having the issue, you start to believe them. But this problem is saying computer to you. So you get on one of the computers that's not working and take a packet capture. You mark that PCAP with a ping and find out where it's failing. Then you look at the TLS with the TLS troubleshooting filter, and sure enough, you see an encrypted alert. You zoom in on one particular conversation by right-clicking a TLS packet and then clicking Follow TCP Stream. See the client reset and export the certs. When you look at the certs, you see that one of them says Untrusted Root. But this is a normal app that should be working, and the name on the root cert looks normal, like it should be a trusted one. Now, back to normal speed. So we have 2 computers not working, and the computer we're on is complaining that the Komodo RSA CA root is not a trusted root CA. So we go to the Windows button here and type MMC and hit enter. Say yes, we want to allow it to make changes. Remember that you need to be admin to see your local trusted root certs. Okay, we're going to click on File, Add Remove Snap-in. We're going to go to Certificates and click Add. Select Computer Account, then hit Next, Local Computer, Finish, click OK. Then we're going to expand Certificates, expand Trusted Root Certification Authority, and then click on Certificates. Now, if we look at the bottom of the window here, it shows the total Trusted Root Certification Authorities that we have in our local computer Trusted Root CA store. If that number is not somewhere around 400, then we've got a problem. If we look here, we can see that we've got 87. And then if we look up here where the Komodo RSA Certification Authority should be, it's not there. So it's really not a Trusted Root CA as far as our computer is concerned. What we need to do is update the list of Trusted Root CAs from Microsoft. Normally when I see this issue, it's a new computer, but it can happen on existing ones too. So go to the Windows button and start typing PowerShell and then click on Run as Administrator. A word of caution here. Even though this is a simple process that I've done many times without issue, there's always a risk. It's always a good idea to make sure data is backed up first. A safer way would be to run Windows Update and let it do this for you, but that is not always an option. The first thing we're going to do here with PowerShell open is to type cd/temp. If you didn't have a temp directory, then you would type md/temp. I get an error here though, because I already have the temp directory. What we're going to do first is grab this first certutil command and copy and paste it. What this did is it went out to Windows Update and grabbed the current list of the trusted root certs and added them to a roots.sst file. We're going to grab this second command here, copy and paste it, and this one is going to add that roots.sst file to an SST store variable. Hit enter there. Finally, we're going to grab this last command and copy and paste it. This command is what actually updates our trusted root certificate store with the information in the roots.sst file that we downloaded with the certutil command. As you can see, all the certs will kind of fly by on the screen there. So now let's open up MMC again and see how many root certificates we have. Click on Add Remove Snap-in, then Certificates. Remember, we're going to select Computer Account, then Local Computer, and hit Finish. And then OK. So expand Certificates, expand Trusted Root Certification Authorities, and then click on Certificates. And if you can see down here at the bottom of the screen, we now have 490 Trusted Root CAs. And let's look for that Komodo cert now. There it is. the Komodo RSA Certification Authority. So we went from 88 trusted root certs to 490. The number can vary depending on what version of Windows you have, but 490 looks good. We try the app again on the computer and it's working. Updating the root certs fixed it. So our connection error message from the app was really not very accurate. Unfortunately, a generic error message like this is frequently all we get from the application. So many times, it's up to us to take a packet capture and really see what's going on. Because if we're not looking at the packets, we're really just guessing. Well, that takes care of the certificate side. Once the root cert is fixed, the app usually stops complaining. But that's not the only strange behavior you might find in a packet capture. What about traffic that shouldn't even be there? Network scans, responder, spoofing, oh my. And a quick security tip while we're here. In most environments, you'll want to block SMB or CIFS traffic going to the internet. Maybe there's a few cases where it's needed, but most of the time, you don't want your users going to the internet to get a file via SMB. So let's take a look at some of that suspicious traffic now, shall we? Users normally hit a few servers at a time. They use names to contact servers for the most part. When is the last time that you saw a non-IT user use an IP address to get to a server? Hackers, on the other hand, especially noisy ones, hit many servers very quickly. This behavior is not natural compared to a user. They leave a trail of evidence or errors in a packet capture. A normal user does not connect to 20 servers in 1 minute, but a hacker may. Hackers will scan your network looking for stuff to get into, just flying around servers and mapping out your network. They will identify servers and their functions for further exploitation. But let's think about even scanning just a single server. There are 65,535 total TCP ports, and maybe 100 ports open at the most usually? Even just scanning that one IP leaves behind a lot of noise in a packet capture. Send packets, and maybe even TCP reset packets. Users do not scan large numbers of ports on a server. Apps that users run don't either. Hackers will send many requests to your DNS servers to find new networks and new servers. And we can see that in a packet capture. They may use Bruteforce, but more than likely they will use word lists containing common names. They will also query PTR records to find server names and functions, because your server's functions, and maybe their locations, are parts of their names, right? You see, all of these things that we do to make our networks easier for us to understand also make it easier for hackers to find what they're looking for. For the most part, user PCs do not talk with other user PCs, they talk to servers. Yes, there are some exceptions to this, but this traffic is always worth investigating. User-to-user file sharing, or SMB traffic, should throw up a red flag. User-to-user port scanning? This is not normal. If user PCs are manipulating services or querying the registry of other user PCs, this is not normal, and it is not user behavior either. So we really want to examine any user-to-user traffic and make sure that it is legitimate. When hackers are scouring a web server looking for something to exploit, you will see a lot of web requests. Word lists of common files leave a big trail in a packet capture that we can easily set up filters to find. Look for a lot of web requests, sometimes even words in alphabetical order, like this. Many times they're looking for vulnerable web pages to attack. Another way web servers are attacked are by logins. If you see many login attempts with many passwords for the admin user, there's no way that a normal user is doing that. Also, maybe many login attempts with many users and passwords. The thing you've got to keep in mind too is the time period. Is an admin user really attempting to log in 20 times in 1 minute? We can also find login errors from all of their bad logins. All of these attempts will leave errors, which will be more of our trail of evidence. Are there tools that allow hackers to force users to log into the hackers? Yes, there are. All of what you're seeing now in orange are usernames and password hashes. This is bad because a lot of the times users use terrible passwords and their password hashes can be easily cracked. But the real question is, does all of this leave a trace in the packet capture? The answer is yes, it absolutely does. Here's what the packet capture looks like. For every username that you see here, there's also a hash in the packet capture. And once again, we are able to filter this traffic and see that it is not normal behavior. Other hacking activity that we can find in packet captures are attacks on Active Directory or manipulation of services. Attacks using built-in tools like Service Controller used over the network can be seen on a packet capture. Again, let's think about it. Does a normal user manipulate services on other PCs or servers? Here we are looking for service controller activity and especially interaction with services with non-standard names. Curb roasting is a technique that attackers can use to attack your Active Directory. They only need one low-privilege account with a valid password to execute this attack. With only this one valid user, they are able to gather all of your service account usernames and password hashes. The hackers can then crack these hashes offline. This is bad, because sometimes as admins we make bad passwords too and give too much privilege to service accounts. But can we find this activity in a packet capture? It's not as simple as other things, but yes, we can. These Kerberos tickets are normally requested by hackers with RC4 encryption, which you will see as ARC4 in a capture. So when we are looking for Kerberosting in a packet capture, we will look for the RC4 encryption. That will be the giveaway. What if you see DNS or DHCP servers that are not your DNS or DHCP servers in a packet capture? The best case scenario where someone has accidentally started these services is bad. It will mess up your network quickly. But the worst case scenario is that you are being hacked. Hackers can use DHCP to redirect your users to their DNS. And if they control DNS, your network is in trouble. And as you can see here, sometimes when your network is being hacked, there's a lot of sparks and smoke flying around in your data center.
Intruder alert.
Or maybe these are their physical network defenses. Also, we will look for IPv6 traffic here. Do you see IPv6 traffic, but you're not using IP version 6? This could be hacking activity too. Something like MITM6, where hackers use IPv6 DHCP to give out IPv6 addresses, set themselves up as the DNS server, and perform man-in-the-middle attacks. That was obvious attacker behavior in that last section. But what about when it's not an external attacker at all? What about when the call is coming from inside the house? Let's take a look at that. You get a call from the help desk. The guy on the other side of the line says there's something wrong with the .50 network. Servers are acting up and users are calling in and complaining. And right after that, Jason over in cybersecurity calls you and says that they're getting alerts on the .50 network. The alerts say port scanning, but it's not really specific. You tell Jason that you'll take a packet capture and get back to him and let him know what you find on that .50 network. Jason seems a little bit anxious and maybe even a little scared. It looks like this might be a real hacker and not a false alarm. So this is our basic network layout. We have three networks, a 192.168.2.0/24 network with an internet connection, and we also have a .50 network and a .100 network. We first get a packet capture of the 192.168.50.0/24 network. We take a full packet capture without filters because we don't know what is doing the scanning and what's being scanned. So what do we do now? I start scrolling through the packet capture and not really seeing anything. Have you ever had this happen in Wireshark? You're just kind of scrolling through packets, looking at the packets on the screen, but not really knowing what to do. This was my experience when I first started learning Wireshark. And yes, there's a lot to learn to it, but you can learn it. Learning Wireshark and networking takes time. But each time you learn something, you will get a bit better and you'll see things that other people cannot see. Then, the next thing you know, people are asking you to look at packet captures for them, and you're the expert. So we think about our signs of NMAP scans. Maybe we look for ICMP timestamp requests. So we use a filter, icmp.type equals 13. Nope, nothing there. Should we look at pings? Let's try the filter ICMP. Do we see many pings in a range of IPs? Nope, I only see 2 pings total. What about pings without responses? Nope, all of the pings that I see here have replies. So let's try something else. Okay, let's change our filter to tcp.flags.send equals true. And then go to Statistics and Endpoints. After that, we'll click on the TCP tab and click on Packets 2 times. So we can sort by the largest number of packets per IP address and port. And be sure that limit to display filter is checked. Now let's look at the top few lines of this table. These are the IP addresses that have the most send packets per port. What we're trying to find here is port reuse, which is our number 2 sign of NMAP scanning. Look at how many more packets are on this first row, which looks like an NMAP scan to me, versus how many packets are on the other rows, which look like normal conversations. So let's put the data from this first row into words and think of it another way. It's telling us that IP address 192.168.2.22 started 1,000 TCP three-way handshakes using a single TCP port 62371. And that is a lot of reusing the same port. So let's select this top line, right-click on it, go to Apply as Filter, and select it. This changes the filter to the 2.22 IP and port 62371. We see that the host potentially being scanned is 192.168.50.240. So now let's change our filter to ip.addr 192.168.2.22 and ip.addr equals 192.168.50.240 so that we can get all the interaction between these two hosts. And let's run through our signs real quick to verify that this is a packet capture. Number 1, many pings or ARP requests. Not many this time, but we do see now where 192.168.2.22 was pinging 192.168.50.240 at the beginning of the scan. So our sign 1 is still good here, because as usual, the NMAP scan starts with either a ping or an ARP request. Number 2, source port reuse. Yep, 62371 gets reused over and over again. Sign 3, time. Well, let's see. We start at 233 seconds, and if we scroll down here, we finish at 253 seconds. So yes, 20 seconds to talk to 1,000 ports. It fits that sign too. What about sign 4, SYNAC retransmissions? Nope, not this time. I don't see any. Or sign 5, a single IP going to the same destination port on multiple hosts. Nope, I don't see that one either, since this is just one host scanning another host. So lastly, what about sign 6, TCP resets? Many TCP resets directed at a single IP from one or more hosts. Yep, I see that one here too. All of the red packets. So this is definitely an NMAP scan. And if we look at the destination ports, you can just see that NMAP is just counting down through the ports like it normally does, starting with 5900, 135, 995, 443, 1720, 25, and 199. That looks exactly like an NMAP scan. And look, here in just a few minutes, we found an NMAP scan and a packet capture of 20,000 packets. Yay! You ask the apps team what the 192.168.2.22 server is, and they say it was a test web server, but it should have been deleted a long time ago. Whenever you hear something like this, be afraid. Be very afraid. It's always the servers that you don't know about, the ones that don't get patched, and that have vulnerabilities. Those are the ones that get you hacked. Now that we know that the NMAP scan is coming from this server, let's hop on over to the .2 network and see what's really going on. We update our network map with the server running NMAP here and our first scan victim here. Next, we will take a capture on the .2 network here where the NMAP scanner is currently running. Now let's take a look at the packet capture on this .2 network, and let's choose another way to find the NMAP scans. We know that default NMAP scans will start with pings or ARPs. So let's put in the filter icmp.resp_not_found, or ARP. These are the IP addresses in a range of IPs that get scanned, but there's nothing there to reply. These unanswered pings are evidence of an NMAP scan. A range of consecutive IPs being pinged seems suspicious. I see a group of these between 50.225 to 50.231, and I also see another group at 50.241 to 50.246. So let's comment the first packet in each group. Right-click the packet and go to Packet Comments and then Add New Comment. On packet 9808, I'm going to add port scan started 50.224 to 50.231. Now I will do the same for the next range of IPs that I found, and I'll label it port scan started 50.241 through 50.247. And I'll do the same with two more ranges of pings that I found that have no response. All of these comments will act as a roadmap for us while we analyze the PCAP file. So now let's look at ARPs, just to see if there's another port scan here somewhere. As I'm scrolling through, all the ARPs look pretty normal up to packet 60123. Then what we see is 192.168.2.22, which we know is our port scanner, is sending out a lot of ARPs starting at .1 and then going all the way to .254 on the 192.168.2.0 network. Since we know that when one machine is counting through the whole network, sending out ARPs, looking for IPs that are out there, is part of a port scan, let's comment packet 60123. Port scan started 192.168.2.0/24. Since we know where our port scanner is from the last section, let's change our filter to ip.addr equals 192.168.2.22. Let's look at another way to see Nmap scans, but this time visually. We can see short bursts of traffic on a graph. I'll go to Statistics and IO Graphs, and I'll also make sure all packets is unchecked and that filtered packets are checked. And again, this is everything coming from or going to 192.168.2.22, which we know is doing Nmap scans on our network. Notice the spikes on the graph. Since we're looking for a lot of packets in a short amount of time, these could be the Nmap scans. If you click on the peaks, Wireshark will move to these packets in our packet list. Let's click on a few and look. Based on the IP addresses that we commented on earlier and all the TCP resets, I can tell that these are our Nmap scans. Let's close IO Graphs and get back to our packet list and put in a filter frame.comment. We highlight our first comment, packet number 9808, and add or ip.addr equals 192.168.2.22 to our filter and hit enter. Notice that when we switch that filter, our commented packet from before is in the center of our packet list. And the reason why we're doing this is so we can see the packets right around that comment. On this screen, let's step back just a little bit and see what's going on. We see a lot of ping packets from 192.168.2.22 and no replies except one from 192.168.50.230. So let's comment this packet, number 9818, port scan of 192.168.50.230. And let's add on to the end of our filter and ip.addr equals 192.168.50.230 so we can see just what's going on between these two hosts. We see that 192.168.2.22 is targeting many destination ports and it's reusing the same source port, TCP 56695. We see a lot of TCP resets, and time-wise, this happens from 138 seconds to 143 seconds. So 5 seconds for 1,000 ports. And we know that's way too many ports in a short amount of time to be normal user behavior. Now let's go back to our comments again by changing our filter to frame.comment. Select the packet 24041, where the second scan starts. Now we put in our filter for our scanner, or ip.addr equals 192.168.2.22, and now that commented packet is in the center of our packet list. We step back again and see a bunch of pings, but only one reply from 192.168.50.240. So let's comment on that one, scan of 192.168.50.240. This 192.168.50.240 is the same target as the very first Nmap scan that we saw. This is the same exact scan, but our capture point is on the 192.168.2.0 network, where that old test web server is that's doing all the Nmap scanning. So let's change our filter back to frame.comments. For these next two comments, port scan started 4.240 to 4.247, and port scan started 5.241 to 5.247. We don't even need to go through those because we're going to add a seventh sign of port scanning. And this one is when networks that are being scanned are not our networks. See, we don't have a 192.168.4.0 or a 192.168.5.0 network. So for this seventh sign, for networks that are not ours, what it really shows is a hacker probing around or looking around for networks. Again, since users are going to mostly use DNS, they're not going to be finding or looking around for any networks that are not there. One caveat to remember when we're looking for port scanning in a capture is that this could always be our own network management or security server. These servers will do a lot of pings and scans. For the last section of this video, let's talk about command and control traffic. In simple terms, command and control, or C2, describes techniques that hackers use to issue commands to and control a compromised server. So in our case, who is controlling this old test web server that shouldn't even exist, that should have been turned off a long time ago? I am. What I'm thinking is that every time we see a scan start, we should see some C2 traffic telling that scan to start. So now let's look right before each scan starts and see if we can find this C2 traffic. Let's highlight our first commented packet, number 9808, and then put in our filter, or ip.addr equals 192.168.2.22. since we know that's where our scans are coming from. Now that our commented packet is in the middle of the screen, what do we see right before that scan starts? I see there's an IP address that starts with 172.27. So now let's keep going and see if that's a regularly occurring IP address or if that's just some random IP address. Let's change our filter back to frame.comment so we can just see the comments again. We will skip over the second comment since it's a part of the first scan range and there should not be a command that directly caused it. So I click on the third comment and then change my filter to or ip.addr equals 192.168.2.22 again. There's the comment in the middle of the screen. And again, right before that comment, we do see the 172.27 address. So now let's go back to the comments and check again. So let's select packet 30595, and then I'll add or ip.addr equals 192.168.2.22 to the end of my filter again. And again, we see the IP address 172.27.72.127 right before the Nmap scan starts. So this is actually looking pretty promising for this being our scanner. So what I want to do next is add a filter that shows the 172 address and all of our comments. So that filter is frame.comment or ip.addr equals 172.27.72.127. So one thing that we can see here is that the first three packets in our packet list are the three-way handshake. We see a SYN, SYNAC, and ACK in those first three packets. So what I want to do here is show only data packets. So I'll just add to the end of my filter and tcp.payload to give me just those data packets. So let's click on one of these blue data packets and then right click and select follow and then TCP stream. What we have here is the data that the hacker is sending in blue and our server's response in red. We can see every command he sent and the results of every scan. In this case, the hacker has compromised our 192.168.2.22 test server, the one that should be down, and it looks like he sent some kind of reverse shell back to his IP at 172.27.72.127. Now this traffic could have been encrypted or using some kind of command and control software, and we might not be able to see the commands, but we should still be able to see the encrypted commands happening right before each of the scans start. Alright, so that covers the scanning side. The internal, the external, and the ones that just hide in plain sight. But scans aren't the only thing that can bring a network to its knees. Sometimes the problem isn't an attacker. It's just traffic. A lot of traffic. So in this next section, we'll look at I/O graphs and how they can show you exactly when things slow down. And more importantly, why. Imagine getting a call from a client with a perplexing problem. Every day at 3 p.m., their network grinds to a halt. They've tried everything. So you step in with your secret weapon, Wireshark's I/O graphs. It's like having X-ray vision for your network, letting you see every spike and every dip in traffic. In this video, I'll guide you through not only reading these graphs, but using them to uncover the hidden mysteries of your network. Alright, now that we know what Wireshark can do, let's actually dive in and start putting this into action. Remember that bandwidth problem that our client has about 3 p.m. every day? Let's take a look at it and investigate and figure out what's going on. The first thing we're going to do is open up I/O graphs, and to do that, we're going to go to Statistics and I/O graphs. So looking at the components of I/O graphs, the x-axis is going to be time, and the y-axis is going to be either packets or bytes. I like to change mine to bits so we can have megabits per second, which we're all familiar with. And something else we want to do in this particular case is check the time of day checkbox, since we're looking for that issue at 3 p.m. that the client's having every day. Now that we see the traffic patterns, let's find out who's behind the data flows. Statistics conversations will give us chat totals between devices, and statistics endpoints will give us totals per device. We open up statistics and conversations, then click on the IPv4 tab and sort by bytes. Here we spot two suspects, 192.168.100.22 and 192.168.2.24. They both send about 2 gig worth of data, but it looks like 100.22 send a bit more. So let's check statistics endpoints in the same way to get the total per device. Aha! 192.168.100.22 sent about 3 gig worth of data. So is this our culprit? Maybe, but let's not jump to conclusions yet. Remember, conversations and endpoints reveal who, but not when, and I/O graphs reveal when, but not who. But let's combine the two to unlock the true power of I/O graphs. To do this, I quickly add two filters, one for 192.168.100.22 and another for 192.168.2.24. I rename each graph and assign distinct colors. Then, I switch the y-axis to bits for consistency. After enabling both filters, I disable all packets. Immediately, patterns emerge. The 100.22 in red shows shorter bursts over a longer period of time, while the 2.24 in blue spikes around 3 p.m., stopping only because I stopped the packet capture. I grab the workstation name for those IPs and point out the red spikes to the clients. This one's from our workstations called Gallifrey, I say. He looks at it and says, yeah, that's my workstation. I ran a few speed tests around 2:45 before we started our testing. I point out the blue spikes from 2.24 and I'm excited. Look at this, I say, this has to be it. The workstation name is INT01. He looks at it. No, that's the intern's workstation, and he's already gone for the day. He leaves every day before 3 p.m. So that can't be it. It kind of seems like you're onto something, but I'm not convinced. I pause considering his point. Even so, let's take a look, because packets don't lie. As we unlock the intern's computer, the issue becomes clear. He has many hefty downloads in progress. What time does he leave again? I ask the client. Around 3 p.m., the client confirms, so I show him the evidence. It looks like he starts up these downloads every day just before heading out. The client's face hardens. All of that lost productivity, he mutters, walking off. I never found out what he said to the intern, but we never got another call about slowdowns at 3 p.m. So that's how you use I/O graphs to see when the network slows down and what's causing it. But graphs only tell part of the story. Sometimes you get issues like the internet works for some people, but not for others. Or a new device that just refuses to get online. Here's a quick networking tip. If new devices can't reach the internet, but existing ones work fine, check your DHCP scope. If it's full, these new devices never get an IP address. Okay, here's the situation. We've just opened up the firewall for a vendor to reach a new application. The firewall rule is simple. Their IP here can access our IP here on port 443. Sounds easy, right? Well, the apps team is just called and it's not working. All they have is a generic connection failed error message and nothing useful in the logs. We take a packet capture at the firewall and open it up in Wireshark. Let's see what's really happening here. We set up our filter for IP.addr EQ 203.0.113.8. This is their IP, and TCP port equals 443. I don't see any packets there, so did they really try to connect? Well, at this point, we could say, we're not seeing any traffic from the vendor on this IP or this port, and just kick it back to the apps team. But let's see if we can figure out what's really going on here. Maybe they're just going to the wrong port. So let's take the port portion off of our filter. So now we just have the IP. And again, nothing, no packets. Maybe they're really not connecting to us. Let's try one more thing though. We know that this vendor owns all of the IPs 1 through 255 in that 203 address space. So let's change our filter to IP.addr equals 203.0.113.0/24. And this will give us all of the IPs 1 through 255 in that network. Okay, here we go. Now we see some packets. But notice all of the source IPs are that 203.0.113.5. It looks like they're coming from the wrong IP, and it's not hitting our firewall rule at all. That's problem number one. Let's also notice something else here. The destination port on all of these packets is port 80, not 443 like it's supposed to be. That's what we told them to connect to. And of course, we're not seeing any replies from our server since that port isn't even open. So we add a few quick comments here and grab a screenshot, and we're going to send it to the apps team so that they can send it on to the vendor so the vendor can fix the issue. The vendor fixes the IP and the port they're using to connect to us, and they try again. The apps team emails you back and says, thanks, everything is working great now. Everything's working again. But before we call it done, we grab a verification capture from the firewall, and this is where things get interesting. So let's use our same filter again. The ip.addr equals 203.0.113.8. And this is the correct IP. And tcp.port equals 443, and that's the correct port. The IP and the port look good, but there's two things that really jump out at us here. Number one, for an encrypted connection, I'm not really expecting to see the words login over here in the info column. And when I click on the packet, this shouldn't be readable because it should be encrypted. That was the GET request, where the vendor side of the app was requesting the login page. And the post here, just a few packets down, is the info that they sent for that login page. I'm a little bit afraid of what we're going to see when we click on the packet, but we click on it and then click on HTML form. Yikes. Username, admin, password, password. And there it is. The login isn't encrypted, and even worse, they're apparently using a default username and password. So you know the apps team isn't really going to love this, but you block access to this new app that no one's relying on yet so that they can fix it. What we want them to do is to force encrypted connections and change that default login and password. Good grief. So they make the changes, we run another verification capture, and the app now is working, but it's not just working. It's working and it's secure. So one problem down, and time to move on to the next one. The apps team calls you back. They're having another urgent issue. The server, the one we just worked on, has been in production for a while, and it has not had any issues with communications. They have some reporting machines on a new subnet, 192.168.3.0/24, the subnet that you recently set up for them. None of these reporting machines can reach this server. This issue is urgent because the first set of reports are due to a client tomorrow. The server team has already looked over the server and tested it, and they don't see any issues. They note that every other subnet can access the server just fine. Any guesses on the cause? To me, this kind of feels like an access list issue, but we'll see in a minute that guessing is just guessing. Let's start by running the same pings the server team did, so we're all on the same page. 3 of the pings work, but 1 ping fails, just like they said. So let's check the access list on the 192.168.3.0 subnet first. Nothing there. Okay, how about on the server side? The 192.168.2.0 subnet. Nope, nothing there either. Well, so much for our access list theory. So if not access lists, then what? Let's start from the perspective of the 192.168.3.179 PC, the one that couldn't ping the server. Let's take a look. We filter for pings by just typing icmp in the filter box. We can see the pings being sent out, but we don't see any replies coming back. So we take a capture from the 192.168.2.25 server while we're pinging from the .3.179 PC. Now let's open up that capture. We filter for icmp again, and we do see those pings getting to the server, but the 2.25 server is not replying, which is kind of weird, right? That tells us that the PC is doing everything it should, but something on the server side is failing. So what should the server do next? Since 192.168.3.179 is on a different subnet, it should be ARPing the default gateway. Let's see if that ARP is present by changing the filter to ICMP or ARP. Well, we don't see any ARPs here from the server to the gateway. Wait though, I do see the server ARPing for 192.168.3.179. Again, weird, right? That would mean the server thinks that .3.179 is on its same subnet. Okay, that's a big clue. Let's RDP to the server and run an IP config, since it kind of seems confused about what subnet it's on. Looking at this IP config, does anything stand out here? Yep, the subnet mask, 255.255.254.0. That's why the server thinks that .3.179 is local. That's why the server was ARPing for that PC. So let's get this subnet mask fixed and test it again. We test it again and everything is good. Good job, we're on a roll now. Hey, the server team just called and they have an issue now. Let's go knock that one out. Just as you were about to finish up on some documentation, the server team calls. They just built a new server and it's working fine, except they cannot connect to it remotely with RDP, Remote Desktop Protocol. So let's see if we can get this solved for them and then get back to our documentation, because it turns out documentation can sometimes solve problems before they happen. Maybe even this one. So first let's test it. We tried RDP from a laptop at 192.168.100.21 to the server at 192.168.50.21. And it doesn't work for us either. We decided to take a packet capture at the laptop, so let's take a look at that now. There's a lot of packets, so let's filter it down by port. We know the port for RDP is TCP 3389, so we use the filter tcp.port EQ3389. And that distills things down pretty well. What we see here is the source IP 192.168.100.21, our laptop, coming from port 50822 and going to the server 192.168.50.21 on port 3389. Then we see that same packet repeat 4 times. Our laptop is sending out the packets and not getting any responses. Are they actually getting to the server? We don't know. All we know is that the laptop is sending out the send packets, which is the first part of the TCP three-way handshake. There's nothing definitive here. So we go take a capture on the server and attempt to RDP again from the laptop. Now let's look at that capture. Wow, over 31,000 packets. Let's filter it down some. So we try tcp.port equals 3389 again. That's better. But let's focus in like a laser and only show the packets we want to see. Let's add to our filter and parentheses ip.addr equals 192.168.100.21 and ip.addr equals 192.168.50.21 parentheses. So we will see only packets that have those two IPs and port 3389 in them. So now what do we see? Packet 1890, the source IP is our laptop, and the destination IP is the server. And the destination port is 3389. It's a send packet just like we saw before. So those send packets that are the first part of the three-way handshake are reaching the server. Next packet, 1891, the source IP is the server, and the source port is 3389, and the destination IP is the laptop. This is a SYNAC packet, the second step of the TCP three-way handshake. Question for you. Did we see these SYNAC packets in our other capture on the laptop? Nope, we didn't. So what is happening to these packets? See the source IP on packet 1892? 192.168.50.1. That's our layer 3 switch on the server side. So let's open it up and take a look. We see type 3 destination unreachable and code 13 administratively filtered. This means something like a router, a layer 3 switch, or a firewall is filtering the traffic. And normally, the device that sends a packet like this is the device that filtered it. So why did this magically appear in our filtered traffic? Is our filter broken? Nope. It's because a type 3 code 13 ICMP packet includes the original IP header and the first 8 bytes of the TCP header. Wireshark sees that as a real IP header, so it shows up in the filtered packets. Now, if we look at the IP and TCP sections below, this is the packet the switch is responding to. The source IP is the server, and the source TCP port is 3389. The destination IP is the laptop, and the destination TCP port is 61015, an ephemeral or random port the laptop used originally. It is responding to our server SYNAC packet. That's what it's blocking. So to summarize, the laptop sends a send packet to start RDP. The server replies with a SYNAC packet saying, okay, let's go. And immediately after that, the layer 3 switch drops the packet from the server and tells the server, hey, I dropped a packet you sent, and this is the one right here. This is why ICMP packets like this are such a goldmine for troubleshooting. An application like RDP won't tell you what went wrong because it can't. You'll never see this error pop up on a screen. But in a capture, it's all there. We SSH to the switch and pull up VLAN 50, the server VLAN. There's an access list on it. And when we dig in, sure enough, it's denying RDP from that server. So we change the access list, send it back to the server team, and they test it. It works, and everybody's happy. Could this really happen? Yes, unfortunately it can. And when we check with the server team, it adds up. They reused an old IP, and years back, they had asked us to block RDP on it for a vulnerability. The real lesson here, keep your ACLs and documentation up to date, or you'll have old rules like this coming back like zombies. All right, that's the full intermediate path. I hope you enjoyed it, and if you're still here, thanks for watching. The big takeaway is this. The more you practice various scenarios, the better you'll get at figuring out what's really going on in a packet capture. If you found this helpful, please let me know. And if you have any ideas for lessons, drop them in the comments. I'm always looking for a good problem to solve. Thanks for watching, and as always, I'll see you in the next one.